each edge in the graph precisely once. And Euler, after whom these circuits are named, he found the necessary and sufficient conditions for a graph to have such a circuit. And the condition is very simple. Each vertex has to have an even degree. And we also discussed an algorithm used a flurry of how to construct such a circuit in a graph which satisfies this condition. There's a small modification of the notion of Euler circuits. We can talk about Euler paths, by which I mean a path from one vertex to a different vertex, which again uses each edge in your graph. So let's write this down as a definition. An Euler path is a path from a vertex to a different vertex that uses each edge in the graph precisely once. Now, and it's not hard to find the necessary and sufficient conditions for such a path to exist. So we'll formulate this necessary and sufficient condition as a theorem. And the theorem says that there is an Euler path from vertex A to vertex B if and only if A and B are the only two vertices of odd degree. There is an Euler path from A to B, where A and B are two vertices, and B should not be equal to A, right? Two different vertices. Different labels usually mean different vertices. If and only if A and B are the only two vertices of odd degree. So in general, what the handshaking lemma tells us, if you sum up all the degrees, it has to be an even number, twice the number of edges. So if you have vertices with odd degree, they will come necessarily in pairs, right? So they can be no vertices of odd degree, two vertices of odd degree, four vertices of odd degree, 6, and so on in general. And if it happens that you have precisely two vertices of odd degree, then the theorem claims there is an Euler path from one of these vertices to the other. And again, the necessity is easy to demonstrate. Basically, the main argument, again, if you construct this path, and then if you happen to pass through a vertex, so you arrive and then you move further on, then you use up two edges, right? So it always decreases the degree of the available edges by 2. And the only time when you don't pass through a vertex is when you just started from your initial vertex, or you just finished in your final vertex, right? And if these two vertices happen to be different, then you see that the degree of those two vertices must be odd, right? Because again, if you pass through them, you use 2, but only when you start out, you use 1. Okay. As for the sufficiency, here we can use Euler's result. So to prove that this condition is sufficient, we'll do the following trick. We'll add by hand an extra edge between A and B. Modify the original graph, call it G, by adding a new edge AB. There could have been some edges already, so we never actually insist in these discussions on having a simple graph. So there could have been some edges between them already, but we add an extra one. So then, here's a caricature of what's 1, 2, 3, 4, 5, something like this. So if this is A and this is B, right? So I've just drawn a few edges attached to A and B. Then what we do, we add an extra edge, and I'll draw it with the blue pen. All right, so, and that you can see makes all degrees even. So this modification we can call the new graph G dashed. I can write it's G union AB. All right, an extra edge. So this new graph has in this new graph each vertex has an even degree. So in the modified graph, each vertex has an even degree. Right? So we only touched one edge, so we only modified the degrees of the vertices A and B. And we bumped them up by 1 unit for A and 1 unit for B. Since they were odd by assumption, now they became even. And now, by Euler's theorem, there exists an Euler circuit. Euler's theorem, there exists an Euler circuit in G prime, or G dash, and that would use each edge precisely once. And we take that Euler circuit and we remove from it this extra edge AB, and that creates an Euler path. Take this circuit, this Euler circuit, remove from it the extra edge at AB to obtain an Euler path. Now again, that's easy to illustrate. So a circuit looks something like this, and it will use in it the extra blue edge. So if I, and it's between A and B, so if I remove it, I get a path. The remaining part of the circuit gives you a path. Quite a simple argument. I'll give you an example. For example, for following graph, explain why an Euler path exists use Flores algorithm to find it. So Flores algorithm was presented as an algorithm to find circuits, but we can do the same thing. We did here, so we can add an extra edge, use Flores algorithm, and then remove the extra edge, right? But in practice, it amounts to the same rule. Take the bridge only when there are no other alternatives. When you execute this for finding an Euler path. And here is the graph. And the vertices labels are A, B, E, D, C, and F. So to argue that it has an Euler path, I have to investigate the degrees of all vertices. So I find that the degree of A is the same as the degree of B is the same as the degree of F, and that those are all equal to 2. Even number. The degree of E is 4, another even number. The degree of D is equal to 3, and the degree of C is equal to 3. So we have only 2 vertices of odd degrees, D and C. So that qualifies the conditions of the theorem. So the answer to the first question is this graph has an Euler path because precisely 2 vertices have an odd degree. And at least it's 2 vertices, D and C. So to find such a path, I have to start at one of them and finish at the other one. It doesn't matter at which one you start, which one you finish, because any path can be always backtracked, right? It can be always reversed. So let me start with D. So I'm going to record my path separately, and as I use up edges, I will be erasing them as the Flores algorithm dictates. So initially, if I start at D, we don't have bridges here, so we go from, say, D to E. Okay, and I erase that edge. No bridges were created. So from E, I can go either to A, to B, or to C. That doesn't matter where I go at this stage. Let's say go to B. I record that, and then I erase that edge. So now I'm at B, and I do have a bridge. BC, the edge BC, right? Because if I remove it, the vertex B will be sitting by itself, disconnected from the rest of the graph. But now there are no alternatives, so I take that edge BC, and also, not to get confused, I erase the 0-degree vertex B. All right, so now, from now on, I'm at C, which is supposed to be my final vertex, but I have not used up all the edges yet. And from now on, well, there are only 2 alternatives here. Either I go from C to E, and then I will be forced to go around this remaining circuit counterclockwise, or I can go from C to F, and then I will be forced to go around this circuit and come back to C clockwise. and it doesn't matter which one we choose. So let's say go clockwise from C to F to D to A to E and back to C. Right, so automatically I finished off at C, at the other vertex of odd degree. And then by erasing everything, you just make sure that we have used up all of the edges. Any questions about the parts? Just a simple modification really of the circuits. Okay, if there are no questions, then let's move on and start talking about Hamilton circuits. What's my next? So Hamilton was another bored mathematician. Like Euler, he was just coming up with some questions which he found personally entertaining. And Euler wanted to create a walk through the bridges in Königsberg, while Hamilton, he created a puzzle, it was called Around the World. So first of all, Hamilton, he was Irish, and he lived in the 19th century. He's probably still the most famous Irish mathematician. So he created a puzzle called Around the World. And he was trying to sell it. So it was a physical object. So he found a manufacturer to produce wooden dodecahedrons. I hope I pronounced it correctly. So what's a dodecahedron? It's a solid body which has 12 faces, right? Like a cube has 6 faces, and dodecahedron happens to have 12 flat faces, and each face is a regular pentagon. Each is a regular pentagon. So regular pentagon. I wouldn't try to draw a 3-dimensional dodecahedron, but I can draw a pentagon, which is a single face. So it has 5 sides, and they're supposed to be all equal. Right? I couldn't draw them maybe quite equal, but they're supposed to be all the same. And so it's a single face is like that, a flat pentagon, and then they have vertices, and when you glue these faces together, at one vertex you glue 3 pentagons. So to this one I would glue one along this edge and another one along that edge. And when you keep gluing that, it closes up. Yeah, it becomes a regular, called platonic, one of the platonic solids. Okay. And so what was in the puzzle, to each vertex there was assigned a capital, one of the countries in the world. And it was written here. And then there was a peg which could be moved along any of the edges along this dodecahedron. And the task was to start at any one of the world capitals, and by moving your peg, visit each other capital precisely once. So that was his puzzle. It didn't sell well, so he didn't gain any money on that. But as a byproduct of this, he left for us this notion of a Hamilton circuit and all the other fun which comes with it, which I'll come soon. So let's first define this. A Hamilton circuit is a circuit in a graph in which each vertex appears precisely once is a circuit in a graph in which each vertex appears precisely once. So, in fact, you can forget about this beautiful dodecahedron, with 12 faces, etc. You can sort of flatten the whole thing and just draw a graph which represents all the edges in this 3D figure, right, which link various vertices. So that would be a graph. And then the task of the puzzle of finding a path, a route through the edges, which would visit each vertex exactly once, is equivalent to finding a Hamilton circuit in that particular graph. But you, of course, now you can formulate this for any graph. Given a graph, can you find a circuit which now visits every vertex precisely once? And it sounds kind of similar to the Euler paths in which you use each edge precisely once, right? But it turns out that here there is no single theorem, like Euler's theorem, which would give us necessary and sufficient conditions for a graph to have such a circuit, right? It's easy to come up with examples, some small graphs for which you can find such a circuit, or vice versa, you can come up with examples of graphs for which it doesn't exist. One thing which is easy to argue is that bridges, again, should be absent, right? So, some necessary conditions are known, like there should be no bridges, right? And then again, it's easy to illustrate. Suppose you have a bridge, and then there is part of the graph on one side of the bridge, right? And then part of the graph on the other side of the bridge, right? So if your starting point was in the left part, then since you have to get to all the vertices, you have to cross the bridge. But then, while crossing the bridge, you would be using this vertex and that vertex, and you cannot use them anymore. So while once you cross the bridge, you cannot come back and close up your circuit. So that's easy to formulate, but that's not the only necessary condition. So in general, we don't know how to characterize what's the set of necessary conditions which turns them into a sufficient condition, for example, right? So some necessary conditions can be formulated, and some sufficiency condition also can be formulated. So there are some theorems which tell you, well, if this graph has this and that property, then Hamilton circuit is guaranteed to exist. But it doesn't tell you that if you don't have that property, then it's not there, right? So there are partial results. So I'm not going to give you any details of those theorems, right? Just kind of outlining the situation. So it turns out to be a different class of a problem, right? Euler's, the problem about Euler's circuits and paths can be completely, explained away. Here, there are only partial results. Let's just write this down. That also some sufficient conditions are known. Right, so I'm not going to discuss more the question of whether it exists or how to find such a circuit. Instead, I'll focus on the weighted version of this question. So for weighted graphs, there is a variant of Hamilton circuits problem, namely find a Hamilton circuit of minimal total weight. Hamilton circuit of minimal weight, right? So often in graph theory, there's a question for ordinary graphs, and there's its notification for weighted graphs. For example, spanning trees. You can ask, well, how to find a spanning tree in a graph, and then if it happens to be a weighted graph, you can impose an additional condition that that spanning tree must have smallest possible weight, and then ask, how do you find a minimal spanning tree? The similar thing happens here for Hamilton circuits. There's an ordinary question like, find a Hamilton circuit, or demonstrate that it doesn't exist. But if it happens that you have a weighted graph, then you can ask whether you can find the one with minimal total weight. And this way we can sort of separate the difficulties. We can ask this question about complete graphs. So in complete graphs, we looked at them a couple of lectures ago, each pair of vertices has an edge between them. So there are plenty of Hamilton paths in complete graphs, right? Because you can travel between each pair, so any order of the vertices, so take a set of vertices, order them in some way, that gives you a Hamilton circuit, right? You can always add the first vertex at the very end, right? Because you can, if you read that string, there are always edges between any neighboring pair, so it's guaranteed to give you a circuit. But then the problem becomes to find the minimal one. And this problem is called the traveling salesman problem. So a version of this, and a further sort of specialization gives us the traveling salesman problem. So the traveling salesman problem says, for a weighted complete graph, and we were denoting the case of n, where n is the number of vertices, find a Hamilton circuit of minimal total weight. So why is it called the traveling salesman problem? Well, you can imagine that, say, this graph, the given complete graph of n vertices represents n geographic locations, which are connected in some way, say by roads or by flights. And then the weights, they characterize these connections. For example, each weight can be give you the total, the distance if you go by car. So what is the total distance between the two given locations? Or if our salesman decides to travel by air, the weights could represent the airfare. And then this traveling salesman wants to visit each wants to start from some location, from some, say, city, fly between the cities from one to another, visiting each one of them precisely once, and then come back to the original point. So that will create a circuit. And this traveling salesman wants, to keep the expenses to the minimum or time travel to the minimum. And that gives you the constraint of the total weight, which either represents the total airfare or the total distance to be traveled, to be as small as possible. Right? So it's a reasonable constraint. So that's the traveling salesman problem. It has other sort of incarnations. For example, in the production of electronic circuit boards. You need to, the machine in a factory needs to drill holes in that circuit board in certain locations. So during the day, there's a drill head which travels from one location to another and drills holes. Right? And it repeats this cycle thousands or tens of thousands of times. So if you want to optimize these, you may want the travel for the drill head to be as short as, the total travel to be as short as possible. So it would be doing these holes as fast as possible. And that's the same problem. For example, you can represent the physical distance between two locations where you have to drill holes as a weight in the weighted graph. And then it can travel between any of them, right? So it's a complete graph where you have an edge between any pair of holes. So it's not a problem to find Hamilton circuit. Plenty of them. We'll soon count all of them. But the problem is to find the one which has the minimal total weight. Okay, so that's just putting this problem. So we're going to focus on this problem. And by the way, note that you might think, okay, so I'm doing, for certain graph problems, I'm doing an ordinary version and a weighted version. So why didn't we do this for an Euler circuit? But for a very trivial reason, because in Euler circuit, if it happens to be for a weighted graph, each edge has to be used up. So the total weight is just fixed. But for Hamiltonian circuit, I'm not supposed to use every edge. Right? I'm supposed to visit every vertex. So some edges will be chosen and some won't. So here it's a meaningless question, right? Because there was no such question for Euler circuits. Okay, so let's first discuss how many different Hamilton circuits there exist for a complete graph K-sub-n. So how many Hamilton circuits are there in a complete graph K-sub-n, right, where we have n vertices. So it's a counting problem, right? How I can think, well, first you may think that, well, I have n choices for the first vertex, and n minus 1 choices for the second vertex, right? And then n minus 2 choices for the third vertex, and that gives us the n factorial. But here, really, it's still an overcount because it's a circuit. So since each vertex appears in it, choosing a starting point doesn't change the actual circuit. Right? It's just a convention where you start. You can think that you start anywhere and then go around it. So that doesn't modify things. So we might as well just choose the starting point, just once and for all. So fixing the starting point which can be any point in a circle, right, gives us, well then I have to choose the first edge, so there are n minus 1 of possible destinations from my fixed starting point, and then from that I have to go to a new vertex that gives me n minus 2, and so on. So that's n minus 1 factorial. And yet this still overcomes, because in principle I have two directions along the circuit. If I already chose a circuit which starts out from some fixed vertex, right, then I can reverse the way I go, and it's the same circuit with the same total weight, just traversed in reverse. So it's the same circuit with the same weight. To identify the circuits which only differ by the direction they are traversed, we divide by 2. And that gives us n minus 1 factorial divided by 2. So that's indeed now the total number of different Hamilton circuits. So that's the total number of different Hamilton circuits. Okay? So imagine now you're given the data, you're given this complete graph Kn, and you're given the weights for each pair of vertices. Right? You're given your weights. So the first idea which comes to mind, if you want to find a Hamilton circuit of total minimal path, can we do it by brute force? So can we find the minimal Hamilton circuit by brute force? By which I mean, let's just list all of them, find the total length for each of them, and then choose the one with the smallest total weight available. And here, it turns out that if you have maybe not so many vertices as you could expect, already say 50 vertices or 30 vertices, it becomes really a no-go approach, right? So, but I'm going to demonstrate this in numbers. I'm going to do an estimate. I would even call it back of the envelope estimate for the feasibility of doing a problem with n equals 50 for a graph with 50, complete graph with 50 vertices, say on the fastest supercomputer. So I'll estimate the time. So let n be equal to 50, and that's sort of a traditional choice because one of the formulations of the traveling salesman problem involved visiting 50 state capitals in the US, where, well, all the, say, road lengths are really known between any two state capitals. So let us estimate time needed to solve traveling salesman problem on a supercomputer. So in the brute force approach, when n is equal to 50, I'll have 49 factorial divided by 2 different Hamilton circuits. So we have 49 factorial divided by 2 different circuits. So let's estimate this number, well, from above. It will be larger than something. And I will work with powers of 10. It's typical for back of the envelope calculation. So what is this number? This is 1/2 times 1 times 2 times 3 times 4. And then, well, there will be numbers greater than 10. Starting, say, with 10, 11, 12, and the last one is 49. Sorry, no commas, just times. And multiplying these numbers in the 49 factorial. And 1/2 we can cancel. And then here, in this list of factors, I find there are 40, essentially 40 numbers, which is yeah. So these factors, there are 40 of them, and each of them will be greater or equal than 10. So this number is huge, big number, but by only keeping the numbers, the factors which are greater or equal than 10, I can estimate that this is greater than 10 to the power 40. A more sophisticated calculation will tell you that it's about 10 to the 63, something like that. But you will see that I won't need this to come to a reasonable conclusion. So this is the back of the envelope, most elementary estimate. So this number is greater than 10 to the 40. Easy to show. Okay. Right. So let me take the fastest supercomputer. And currently, it's called, the supercomputer, which is considered to be the fastest, called Summit. And yeah, it's located somewhere in the US. There's always some competition, but it changes time to time, but at the moment this is Summit. And the speed of supercomputers is characterized in something which is called petaflops per second. So we'll explain what it means, but let me write this down. So its speed is 143.5 times to the 10 to the 15. So, well, so this is called pentaflops. 143.5 pentaflops. So what penta means, 10 to the 15. So it's equivalent to saying it does 143.5 times 10 to the 15, power of flop stands for the floating point operation, and S stands for second. So floating point operations per second. So floating point operation, it's an arithmetic operation like addition or multiplication, but it's done with numbers packaged in a certain way that allows you to handle very long numbers, sorry, very large numbers or very small numbers. So obviously, if you need to add up two numbers, the time you will spend on it depends on how big these numbers are. So this floating point, I'm not going to explain any details, but it's something, it's some method of handling very small and very large numbers with many, many digits. Okay? And then this computer can do this many operations on these numbers of large sizes in terms of digits per second. Well, we need to, what do we need to do? We need to list a particular Hamilton circuit and then add up all the weights in it. Right? There are not that many weights. There are only right, 50 weights will be involved. So you need to add up 50 numbers. So there are a certain number of arithmetic operations involved in handling each circuit. Now, I'll be very optimistic. I'll assume that, well, instead of, this is just a single, number of elementary operations. So let's assume that the computer can handle this many circuits per second. Right? This is more optimistic. I'm always on the optimistic side. Right? So assume the computer can handle, well, 143.5 10 to the 15 circuits per second. It will be a bit less, right? Because it will need some floating point arithmetic operations for each circuit, some number. But optimistically, that's okay. And moreover, I don't like this number 143.5 for my back of the envelope estimate, so I will take a bigger number. So even better, even more, let's assume 200 times 10 to the 15 circuits per second. Even more optimistic. So now, what will be the time I'll spend working through my graph? So I'll take the total number of circuits, which is greater than 10 to the 40, and divide it by the number of circuits I can handle per second. So divide this by 200 times 10 to the 15. So this gives me an estimate. So I will spend at least this many seconds solving the problem by brute force. So at least we will spend this many seconds. So here I can tidy this up a little bit. So it's 0.1 half is 0.5. 10 to the 40 divided by, there are two zeros here, so it's 10 to the 17. So it's 0.5 times 10 to the 23. Or I can write it as 5, which is a number less than 10, times 10 to the 22 seconds. And it's hard for us still to comprehend, is this a lot or not so much in seconds, right? Because, for example, maybe it's 1 year, or maybe it's a few years. Let's convert this to years. So in 1 year, we have 365 days. There are 24 hours in each, 60 minutes in each hour, and 60 seconds in each minute. So that, if you multiply through, this gives you 31,536,000 seconds. And that's, I can round this up to a larger number, so that's less than 4 to the 10 to the 7th, right? So we'll round this to 4, and then I have 1, 2, 3, 4, 5, 6, 7 zeros. Just counting the zeros. And therefore, the number of years in 5 times 10 to the 22 seconds is at least this number divided by 4 to the 10 to the 7th. Right? So I'm dividing the total number of seconds by the number of seconds in a year. And since I estimated this from above, right, the actual number, which would be, if I take literally that, will be even bigger. All right, but this is a nice calculation. So it's 5 quarters times 10 to the 22 minus 7. That's 10 to the 15 years. Right? So for comparison, the age of the universe from the Big Bang is 10 to the 10 years. For comparison, the age of the universe from Big Bang is about 10 to the power 10 years. Right, and we have 100,000 ages of the universe. So that really nailed it, right? There's no way, even if I had, 100 of such supercomputers, or 1,000, you name it, even if I was willing to wait 10 years for the calculation to finish, still nowhere near the capabilities of our computers. And it's very interesting, right, that the input data is really small. You have, a graph with 50 vertices. That's nothing in modern terms, right? 50 vertices, and there are distances between, or weights between each pair. It's a very small input. Very easy to write a program, which would generate these Hamilton circuits one after another, find the total weight. Well, you know that your program will never ever stop. Not in your lifetime, definitely. You'll never finish the course. So it's very interesting that such kind of a small input data generates such complexity. And on the other hand, if you have a graph with 5 vertices, you can do it with a pencil and paper. So it's interesting where the boundary is. When you need a few seconds to solve the problem, and you need the age of the universe. So the boundary currently is somewhere sort of in the 20 vertices. So say you can do maybe 20 vertex graph problem in a year, but then it leaps beyond and beyond. Okay, sorry, I did 2 minutes.